All right, let's quickly go over Excel's normal distribution functions before we actually start using them. And the idea is for you to use this as a cheat sheet, so I'm not going to go into a ton of detail into each function right now, as I will break them down individually later. But overall, we've got these 5 functions that help make calculations related to the normal distribution. First, we've got the norm.dist function, which stands for normal distribution, and that one basically helps calculate probabilities for values in a normal distribution. Then the norm.inv, or inverse, does the opposite. It returns a value from a normal distribution based on a probability. Now the standardized function we've already seen. It's for calculating z-scores. And then we have the norm.s.dist and norm.s.inv functions, which are the same as the first two, but for the standard normal distribution. So this uses z-scores instead of x values, and always has a mean of 0 and a standard deviation of 1, which is why you don't see those arguments in these functions. So again, those are the functions that we'll be using, which I will cover in depth as we start to apply them. Alright, time for the fun to start. If a variable follows a normal distribution, then you can calculate the probability of randomly obtaining a value within a specified range. And this probability, if you recall from the distribution types lecture, is determined by the area under the curve in that range. Now, if you took a stats class in high school or in college, then this is typically when the integral calculus came knocking at the door, or rather came and knocked you out. At least it did with me. But because of the Excel functions that I introduced in the last lecture, we're not going to need any calculus, so no need to worry about that. Now, there are 3 types of probabilities that we can calculate here. Number 1, the probability of getting a value less than or equal to a value x. And this area, which goes from negative infinity to our value of x, is what's known as the cumulative probability. Now 2, we can calculate the probability of getting a value between something like x1 and x2, and the area here is actually the cumulative probability of x2, so all the area all the way from negative infinity on the left up to x2, minus the cumulative probability of x1. And 3, we can calculate the probability of getting a value greater than or equal to x, or x2 in this case. And here the area is 1, or 100%, which represents the entire area under the curve, minus the cumulative probability of x2, which again is the area from negative infinity to this x2 value right here. Now, we'll see multiple examples of these, so don't worry if this doesn't stick yet. And you may have noticed this already, but you cannot calculate the probability of obtaining an x value exactly, since there's no area under a single point. So if we think about our MBA grade example, which is the variable that so far we've assumed is normal, well, we can calculate the probability of a student getting a grade less than 90, or getting a grade between 89 and 91, or getting a grade greater than 90. But we can't calculate the probability of a student getting 90 exactly. Okay, time to revisit these Excel functions so that we can actually start calculating some probabilities. The norm.dist function returns the cumulative probability, or the probability density, at x from a normal distribution. And to understand it a little better, let's take a look at its components. X is going to be the value to calculate the probability for. These 2 arguments are the mean and the standard deviation that describe the normal distribution of your population. And the final cumulative argument has 2 options. If you select true, it returns the area under the curve from negative infinity up to that x value, which as we now know is the cumulative probability. And if you select false, it's just going to return the height of the normal curve at that x value, which is otherwise known as the probability density. So let's test this formula out on this possible question. What's the probability of an Olympic basketball player being 2 meters tall or shorter? Okay, well first let's look at the population of basketball player heights, which is this one that we have right here, that we know is normally distributed with a mean of 195.2 and a standard deviation of 10.26. So if we want to calculate the probability of a player being 2 meters tall or shorter, that's the same as saying that his height is going to be less than or equal to 200 centimeters. So what we want is this area right here from negative infinity to 200. And to calculate that, we can use the norm.dist function. The x is going to be 200. The mean, as we know, is 195.2. The standard deviation is 10.26. And since we want the area under the curve, then we'll write true as the final argument, which gives us this value of 0.68 or 68%. That's the probability. That's the answer to this question. But what if we had written false instead of true though? Well, then we'd get a value of 0.035, which is just the height of the curve at x equal to 200, as you can see on the chart here. And if you're wondering why Excel even gives you the possibility to calculate the height of this curve, it's precisely so that you can plot these charts using those values. It's how I got the screenshots for this course actually, and I'll show you how to do that very soon. But for now, let's stick to the areas under the curve or the cumulative probabilities. That's what we're interested in. All right, next question. What's the probability of an Olympic basketball player being between 1.9 and 2 meters tall? Well, to calculate that, we first need to calculate the probability of him being less than or equal to 200 meters tall, which is that 0.68% value that we just got. Then we calculate the probability of him being less than or equal to 190 centimeters tall, which is this right here, or around 0.3061 or 30%. And then we just subtract those two values, giving us this area here. And this is precisely the probability of an Olympic basketball player being between 1.9 and 2 meters tall, so around 37.3%. All right, final example before we jump over to Excel. What's the probability of an Olympic basketball player being at least 2 meters tall? Well, we know the probability of him being the opposite of that, so 2 meters tall or less. So all we need to do is just 1, which is all the area under the curve, minus that, and then get 0.32, giving us the final probability of 32%. Awesome. All right, now let's go actually do this in Excel ourselves. I'm going to go to the calculating probabilities with the norm.dist function link. Click on that. And we want to know what the probability is of a graduate getting a final grade of 70 or lower, since that's a pretty subpar score. Well, we know that this variable is normally distributed with this mean and this standard deviation, so we're good to go here. We can calculate this probability. The x is going to be 70, and we want the probability of getting a value less than or equal to that, so the cumulative probability of negative infinity all the way up to 70 straight up. So we can use the norm.dist function for that. So norm.dist, our x value is this 70 here. This is the mean for our normal distribution. This is the standard deviation. And we want the area under the curve, so we want to select true here. Close our function, press enter, and we get 4.97. How easy was that? So now we know that close to 1 out of every 20 students is going to get grades of 70 or lower under our current program. Okay, so we just covered the norm.dist function. Time to go over norm.s.dist, which is actually very similar. Now the norm.s.dist function returns the cumulative probability or the probability density at z from the z distribution, otherwise known as the standard normal distribution. And if we look at the arguments, you'll see that we have z instead of x, which is the z-score to calculate the probability for. And we don't have the mean and standard deviation arguments here, since the z distribution always has a mean of 0 and a standard deviation of 1. So we're just left with the same cumulative argument, in which true returns the area under the curve and false returns the height of the curve. So a possible question here would be something like, what's the probability of an Olympic basketball player being at least 1.5 standard deviations shorter than the mean? Alright, so we've got the standard normal distribution and want to calculate the probability of getting a z-score less than or equal to negative 1.5. So we want this area right here, which makes the function pretty easy. We just write norm.s.dist, we add the negative 1.5 for the z-score, and the true returns the area under the curve, which in this case gives us a probability of 0.066 or 6.6%. And if we had done false instead, then we get 0.13, which is just the height of the curve. Again, not the probability. So very similar process. Granted, these sorts of questions are less common and less intuitive than the ones that we saw in the previous lecture, but it is important that we start getting used to this function and calculating probabilities based on z-scores, since it's going to come in very handy when we're doing hypothesis tests. So let's quickly head over to Excel and go over an example. Alright, here in Excel, I'm going to go through the link on calculating probabilities with norm.s.dist, and let's see what we need to do here. What is the probability of a graduate getting a final grade 1 standard deviation away from the mean at the most? Alright, so that means that we need to calculate the probability of getting a z-score between negative 1 and 1, which means 1 standard deviation away from the mean. So the lower value is going to be negative 1, the upper value is going to be 1, and remember that in these cases where we want to calculate the probability between two values, we need to calculate the cumulative probability for the higher value first, and then subtract the cumulative probability from the lower value. So let's write our norm.s.dist function. The z upper is going to be this one, so 1. And we want to return true because we want the area under the curve. And then we just subtract, again, norm.s.dist, z lower, true, press enter, and we get a probability of 68.27%. And this may start ringing a bell. It might look a little bit familiar, or at least it should, because it's the same exact percentage from the empirical rule, which outlines that around 68% of the values live 1 standard deviation away from the mean. This is where that comes from. Pretty cool, right? Alright, time to test your knowledge with an assignment on calculating probabilities with the normal distribution. Molly's back with another email, this time on the subject of honor students. So here's what she has to say. I keep thinking about the possibilities now that we know that the grade averages for our graduates follow a normal distribution. For example, I'd love to consider anyone that graduates with an average of 90 or higher an honor student. What would be the probability of someone getting that grade? Because I'd hate for it to be more than 10% of the students. Alright, so only one key objective here. Use the norm.dist function to calculate the probability of getting an MBA grade higher than or equal to 90. Good luck!